A lot of linear algebra is about matrices, so we're going to walk through some definitions of what a matrix is and some matrix algebra, multiplication by scalar, addition, subtraction, matrix multiplication, and how we look at linear systems of equations in matrix forms. So a matrix is a rectangular array of mathematical things, usually numbers, like this written before, like we've seen before, like a coefficient matrix. So that's a matrix. So what's the various notations going on here? So two matrices are equal means that each corresponding term is the same. So here we must have A11 equal to 1. So this term has to be equal to that term. And A23, that's this term, that has to be equal to 4. And A34, that has to be equal to 1. All right, so equality means corresponding entries are equal. And generally, when we're writing these out, we use this kind of a notation. For each of these, the first number is the column, and the second number is the row. Sorry, I got that backwards. The first number is the row, the second number is the column. So this is the element in the first row and first column, 1, 1. This is the element in the second row, row 2, and it's the third element. It's in the third column. So row 2 is here, third column. Row 3, column 4, A34. So row by column. This matrix M is a 3 by 4 matrix, right? It's got 3 rows and 4 columns. And that's what the size of a matrix is. You specify the number of rows and the number of columns. And we do it in that order, rows and then columns, although it's easy to get backwards. Zero matrix, all entries equal 0. So there are many different ones because each size has its own zero matrix. So a 2 by 2 zero matrix means 2 rows, 2 columns, right? 4 by 1 means I've got 4 rows and 1 column. So 0, 0, 0, 0. That's also called a vector, right? And we can have, say, a 2 by 3 zero matrix. I'm going to have 2 rows, but 3 columns. So 0, 0, 0. There's 1 row, 0, 0, 0. There's the second row. So every size has got its own zero matrix. So multiplication by scalar. Scalar is another word for number. And our scalars will be generally real numbers and occasionally complex numbers. We have lots of words that mean the same thing in math, but in different contexts. So scalar and number appears the same thing. As you generalize in more abstract algebra, you can generalize number in a lot of different ways. Scalar is one particular way to generalize that. And so multiplying a matrix by scalar means multiplying each element of the matrix by the scalar. And you can factor things out. So what's minus 2 times m? Well, it'll give us a matrix of the same size, but everything will be multiplied by minus 2. So our first row, minus 2 times 1 is minus 2, minus 2 times minus 3 is 6, minus 2 times 5 is minus 10, minus 2 times 7 is minus 14. You can guess what the next row is going to look like. And then finally, the last row will be 8, 6, 0, minus 2. So we can just multiply each element by minus 2. And likewise, you can always factor out an integer, or any number, but you have to be able to factor it out from each element. So what can I factor out of here? So I can factor 6 out of that. So M is going to be equal to 6 times 2 minus 1, 6, 0, minus 2, 3. Right? So we just factor 6 out of that, and we can put it out front. So factoring in and out of numbers, you just have to remember that it has to happen to each and every element of the matrix. Addition and subtraction matrices, they have to be the same size to add and subtract. And you just add and subtract corresponding entries. So M1 plus M2, this is my matrix M1, this is my matrix M2. What's that going to be? We're going to have one big matrix. 1 plus 3 is 4, minus 3 plus minus 4 is minus 7, 5 minus 2 is 3, 7 plus 6 is 13. 2 plus 4 is 6, 0 plus 0 is 0, 4 plus minus 5 is minus 1, 3 plus minus 2 is 1, minus 4 and 7 is 3, minus 3 and minus 10 is minus 13, 0 and 0 is 0, 1 plus minus 1 is also 0. So we just add the corresponding entries, and they have to be the same size. So the additive inverse is just a matrix multiplied by minus 1. So if we take M2 and we want its additive inverse, we just get minus 4, 0, 5, 2, minus 7, 10, 0, 1. We just take this matrix and multiply everything by minus 1. And of course, when I add M2 and minus M2 together, what do I get? I get the 0 matrix. Right? M2 minus M2 equals 0. Okay, finally, matrix multiplication is a little more complicated than addition and subtraction. You multiply the rows term by the columns. So this is a 3 by 4 matrix. This is 4 rows and 2 columns. It's a 4 by 2 matrix. So the product is going to be something. But how do I do multiplication? I take this first row, the 1, and I multiply by the 1. And that gives me 1. Then I take the minus 3 times the 5, and that's a minus 15. I take the 5 times the minus 1, that's a minus 5. And I take the 7 times the 0, and that's a 0. So I took each element of this row and multiplied it by each element of this row this column going down. Then I do the same thing for this row and the second column. 1 times 3 is 3. Minus 3 times 0 is 0. 5 times minus 2 is minus 10. 7 times 1 is 7. Great. So that's the first row. First row times first column, first row times second column. Now we'll take the second row and multiply that by the first column. We'll put the entries down here. So we get 2 times 1 is 2, plus 0 times 5 is 0, plus 4 times minus 1 is minus 4, plus 3 times 0 is 0. Second row, second column, 2 times 3 is 6, plus 0 times 0 is 0, plus 4 times minus 2 is minus 8, plus 3 times 1 is plus 3. Third row times first column, minus 4 times 1 is minus 4, minus 3 times 5 is minus 15, 0 times minus 1 is 0, 1 times 0 is 0. And then third row times second column. Minus 4 times 3 is minus 12, minus 3 times 0 is 0, 0 times minus 2 is 0, 1 times 1 is 1, right? So this was taking the first row times the first column, right? So we took the first row of this times the first column of this, and that gave me this. First row of this matrix on the left times the second row gives me this, right? And then the second row times the first column was this one. The second row times the second row column gave me that one. And finally, the third row, this one, times the first column gave me this, and then the third row times the second column gave me that. And we can actually sum all that up. This is 19, 0, minus 2, 1, minus 19, and minus 11, I believe. Great. And note that this is a 3 by 2 matrix. Because we had 3 rows multiplied by 2 columns, and we ended up with 3 rows by 2 columns. So we can take a 3 by 4 matrix, and we can multiply it by a 4 by 2 matrix, and the result is a 3 by 2 matrix. Note that these have to match to be able to do the multiplication. I have 4 entries in each row, 4 entries in each column, and I multiply down, and that's what we get. So that's how matrix multiplication works. It takes a little practice to get used to it, though. So the rows in the matrix on the left have to have the same number of entries as the columns on the right. And if we have an M by N matrix and M2 is a P by Q matrix, then N and P have to be the same to be able to multiply it out. And the result is going to be an M by Q matrix. Is matrix multiplication commutative? Well, no, right? If we have these two matrices, from the previous problem, we had a, what was that? 3 by 4 times a 4 by 2. And that gave rise to a 3 by 2 matrix. If we tried to switch the order, we'd be multiplying a 4 by 2 matrix by a 3 by 4 matrix. And you can't even multiply them together. So in the previous problem, right, the first matrix can be multiplied by the second matrix, but the second matrix can't be multiplied by the first matrix. But it's even worse than that. If you have two matrices that can be multiplied in either direction, they might not actually multiply out to be the same. What's M1 times M2 here? Well, this is a 2 by 2 matrix. This is a 2 by 2 matrix. So we're going to get a 2 by 2 matrix as a result, right? These two are the same, and so we'll end up with a 2 by 2. And it would be 1 times minus 1, which is minus 1, and I should give myself more space. First row times first column plus 2 times 3, which is plus 6. And then first row, which is 1 times 0, which is 0, plus 2 times 5, which is 10. Second row times first column will give me minus 3 plus 12. Second row times second column will give me 0 plus 20. So what matrix is that? 5, 10, 9, 20. What's M2 times M1? Well, we'll rewrite this here because we want to make sure it's in the right direction. Minus 1, 0, 3, 5 times 1, 2, 3, 4. What's that going to give me? Minus 1 times minus 1, first row times first column, minus 1 times minus 1 plus 0 times 3 is minus 1 plus 0. Minus 1 times 2 is minus 2 plus 0 times 4 is 0. 3 times 1 is 3 plus 5 times 3 is 15. And 3 times 2 is 6 plus 5 times 4 is 20. And what do we end up with? Minus 1, minus 2, 18, and 26. So the order in which you multiply your matrices is important, right? Which one's on the left and which one's on the right is an important thing there. Great, so a little bit about matrix multiplication, addition, subtraction. Note, we haven't talked about division yet. So if we think of vectors as n by 1 matrices, so here's a vector, we can actually write matrices in a matrix form and matrix equations as systems of equations. So we can turn this into a systems of equations because we now know how to multiply this 3 rows onto 3 rows by 4 columns times 4 columns by 1 thing. So we get 1x1 minus 3x2 x1 minus 3x2 5x3 7x4 and then 2 times x1 0 times x2 4 times x3 3 times x4 and then finally third row against the column minus 4 times x1 minus 3 times x2 0 times x3 plus x4 1 times x4 equals 5 7 1. Technically this should be a matrix and this should be a matrix, but these are both 3 by 1 matrices. And if they're equal to each other, that means that the corresponding elements, which is this equation, equals that. So these are the coefficients. These are the variables. Not really any name for that. We'll call it the right-hand side. And this is VAR, my variable matrix. So coefficient matrix times variable vector equals the right-hand side. And we can turn this into matrix form. Our matrix of coefficients is 2, 8, 3, 1, 3, 2, 2, 7, 4. Our variables are x1, x2, and x3. And our right-hand side is 2, 5, 8. And so investigating the properties of the coefficient matrix tells us a lot about how we can solve systems of equations.